So when you activate the insulin receptor, you activate the tyrosine kinase activity of that receptor. I want you to appreciate that in that beta subunit shown here, this is again a polypeptide. There are several tyrosine residues, part of that polypeptide. They get phosphorylated by the intrinsic kinase activity of the receptor. That's called autophosphorylation, meaning the receptor phosphorylates its own subunits on specific tyrosine residues. These aren't loose tyrosines. They're part of the receptor itself, of the polypeptide making up the beta subunits. Very important. So that is a sign that the receptor has been activated. In the well-fed state, insulin rise in the plasma can reverse the effects on the phosphorylation status of specific enzymes by activating a phosphoprotein phosphatase, which will remove specific phosphates from serine and threonine residues that were previously added by protein kinase A or pKa in the fasting state. This effect of insulin on protein dephosphorylation is a consequence of the insulin receptor initiating a cascade of events intracellularly that activate a phosphoprotein phosphatase. Through a cascade of post-receptor events, insulin activates a phosphoprotein phosphatase of 5 key enzymes and activates them. Dephosphorylation of glycogen synthase activates the enzyme and increases glycogenesis. Dephosphorylation of PFK2 and pyruvate kinase will activate glycolysis. Dephosphorylation of HMG-CoA reductase, the rate-limiting enzyme in cholesterol biosynthesis, will activate cholesterol synthesis. And dephosphorylation of acetyl-CoA carboxylase will activate fatty acid synthesis in the liver as well. Through a cascade of post-receptor events, insulin inhibits 3 enzymes by promoting their dephosphorylation. Those 3 enzymes are fructose bisphosphatase 2, glycogen phosphorylase, and hormone-sensitive lipase. Inhibition of fructose bisphosphatase allows the accumulation of fructose 2,6-bisphosphate required for activation of glycolysis and PFK1. Dephosphorylation of glycogen phosphorylase inhibits it and inhibits glycogenolysis. Dephosphorylation of hormone-sensitive lipase inhibits lipolysis of stored triacylglycerols in adipose tissue. In the well-fed state, a rise in plasma glucose elicits the release of insulin, which will then activate the insulin receptors in many tissues. Activation of the insulin receptor elicits a plethora of intracellular responses, including 3 anabolic responses, which are synthesis of glycogen from glucose, synthesis of triacylglycerol from fatty acids, and synthesis of proteins from amino acids. In general, insulin will promote the synthesis of glycogen from glucose, the synthesis of triacylglycerol from fatty acids, and the synthesis of proteins from amino acids. So we're going to go into the specific effects of insulin, and first on carbohydrates. So there are really a variety of things that get activated, a variety of things that get inhibited. What gets activated is glycogen synthesis and glycolysis, two processes that consume glucose because there's plentiful glucose in the bloodstream. Okay? The reverse processes, glycogenolysis, which produces glucose, and gluconeogenesis, which also produces glucose from smaller molecules, are inhibited. And that's specifically important in the liver, because the liver is the only tissue that has gluconeogenesis. In both liver and muscle, you have a decrease in glycogenolysis, degradation of glycogen. The tissue-specific effect of insulin is this last one. This should be really highlighted, very important. Insulin stimulates glucose uptake in these specific tissues, muscle and adipose tissue, by increasing the number of GLUT4 transporters on the cell surface, in the cell membrane. So more transporters, more glucose taken up into the cell. Adipose tissue, or effect of insulin on lipid metabolism. Let's start with adipose tissue. You remember, adipose tissue is where we store a lot of tags. The adipocyte is roughly 80% tags. Okay? So adipose tissue, important effects on adipose tissue is first to decrease lipolysis by inhibiting hormone-sensitive lipase. Second is you increase tag synthesis. And how are tags synthesized? That you need fatty acids and you need glycerophosphate. The fatty acids are coming from the dietary tags from chylomicrons. Lipoprotein lipase breaks them down, picks those fatty acids up into adipose tissue. Then they are esterified to glycerophosphate. Where is the glycerophosphate coming from? It's coming from DHAP from glycolysis. So remember, adipose tissue picks up glucose. It's using glucose for its own energy needs. So it will have an ample supply of DHAP and glycerophosphate as a result. And that's the backbone used to esterify fatty acids from the diet, or from de novo synthesis from VLDL, and you increase tag synthesis. One important positive effect of insulin, this is very important, is that it can upregulate lipoprotein lipase. This is a distinct lipase from hormone-sensitive lipase. It's distinct in its location and it's how it's regulated. It is part of the endothelium, so it kind of hangs out attached to the endothelium wall, if you want, and the enzyme can access the lumen of the bloodstream and access chylomicrons and VLDL. So it chews on those to be able to pick up fatty acids to be stored in the respective tissues. used or stored. Okay, so this is important effect of insulin. In most tissues, as I mentioned, so here we have TAG increase, synthesis of TAG, decrease lipolysis. The other class of molecules, proteins, you're going to basically increase protein synthesis in most tissues because there's plenty of amino acids in the bloodstream when after a meal, and all the tissues will try to pick them up to replace what was turned over in a prior cycle. Importantly, though, the muscle will use up a lot of those amino acids because of its mass. Okay? But as I mentioned again, you have three things that are stimulated: glycogen synthesis, TAG synthesis, and protein synthesis, all by insulin. And this is really a summary table of the effects of insulin. Very important. Without getting into all the details, but here's the first important effect. Note where the checks are. Muscle, adipose tissue only. Not the liver. The liver will pick up glucose, but not because of insulin, because of high glucose. The liver transporter is GLUT2, and that is a low affinity transporter. That means it doesn't have a high affinity for glucose. So, but when glucose rises in the bloodstream, the liver will start to pick up more of that glucose. Okay? Cellular respiration, what does that mean? If you don't understand what cellular respiration, maybe you missed a couple of lectures. That's the ETC, electron transport chain. That's where we're using oxygen. Why do we need the ETC? Because most of the metabolic pathways, catabolic pathways that produce energy, like glycolysis, PDH and TCA, produce NADH and FADH2. And you need to take those high energy molecules, oxidize them through electron transport chain to produce ATP. So as a general rule, insulin is going to stimulate cellular respiration, production of those high energy molecules and their eventual production of ATP. Stimulating glycogenesis, that's in liver and muscle. Inhibiting glycogenolysis, that's in liver and muscle. Stimulation of amino acid uptake. The muscle is a key tissue, but really there's going to be increased uptake in other tissues as well. Protein synthesis is stimulated throughout most tissues, inhibiting protein degradation. TAG synthesis is specifically increased in liver and adipose tissue. You inhibit TAG lipolysis, specifically by inhibiting hormone-sensitive lipase in adipose tissue. And this is really important in that this allows lipoprotein, or lipase is responsible for accessing fatty acids from circulating tags in the form of chylomicrons and VLDL. There's an upregulation, meaning there's an increase in the amount of lipoprotein lipase on the surface of endothelial cells. If you like this video, please subscribe. Thank you.